Okay, so you may have heard of the halting problem before. What is the halting problem? Restated in the terminology we've used so far, it's basically asking, does there exist some Turing machine H such that the language of H is all tuples M and W such that M given the string W halts? Well, it's actually a little bit more complicated than that. So this is our first attempt at defining what the halting problem is. Turns out you can actually do this, and here's how you do it. The Turing machine H reads in M and W and just runs M of W. If M of W halts, then H accepts. If M of W doesn't halt, then H will be waiting forever till the end of time for an answer. Doesn't seem like a very satisfying answer, right? I mean, I already know I can check a halting problem halts by just running it and waiting for it to halt. But some halting programs take a really long time to halt, and it'd be nice to know ahead of time if they're going to run forever or they're just going to run for weeks and weeks and weeks, right? So this doesn't feel like a very useful in the spirit of the answer. This is a kind of halfway answer called and we call this language recursively enumerable. We'll get to that definition later. I'd like a more strict definition. I would like a machine H that's defined as follows. H takes in an encoding of a machine M and some string W, and it accepts if M of W halts and returns whatever, and it rejects if M of W ends up stuck in an infinite loop. How H works we don't know, but H is some magic oracle that just looks at the Turing machine M and the string W and magically divines, using its magic powers, whether the machine will halt or whether it will run forever. Okay? We're going to assume such a H exists and then prove by contradiction that it can't actually exist, right? So we're going to prove the halting problem by contradiction. Does there exist some basically finite decision process that takes a Turing machine, gives it some input, and decides in finite time, guaranteed always, whether it will halt or not? It turns out not to be the case, so let's prove it. So we'll assume the halting problem can be solved. So if the halting problem can be solved, that means H exists. Solved. So H exists. This machine H exists. I'm going to define a new machine P in terms of H. So I'm going to define P. P takes a single encoding of a machine T. And what it does, it halts and accepts, or halts and accepts, halts in an accepting state if you prefer. If H fed the machine T and fed the encoding of the machine T as input, halts. Rejects. Otherwise, P itself gets stuck in an infinite loop. If H of T fed T accepts. So what P does, P takes a Turing machine T and asks the halting oracle if T fed into itself halts or not. So if T fed into itself loops forever, because the encoding of T is some string, right? So I take the Turing machine T and I feed it the encoding of itself. If H rejects, that means T does not halt on itself, T loops forever on itself. If that's the case, then P halts. If T halts on itself, then H accepts, and then P will run forever. And the question is, what does P fed itself do? So what does P fed the encoding of P as input do? All Turing machines have some encoding as a binary string, so if H exists, then P exists, so P has an encoding as a binary string. My question to you is, what happens if we feed P the encoding of P. So maybe pause the video for a moment and just try by cases, right? I mean, this thing either has to halt or it doesn't, right? It's either going to run forever or it's going to halt. So try proving both cases are impossible. So have a go doing that. Okay, I'll assume you have a go at that. So we've basically got two cases to consider. P fed P runs forever and P fed P halts. So we'll try the case P fed P gets stuck in a loop forever. Okay, when would that occur? It would occur when H fed an encoding of P and an encoding of P as input. So H is fed a machine P and the encoding of P is an input string, and that must have accepted. Okay, if H of P and encoding of P accepts, what does that mean? That means, yep, so we assume P of P runs forever. That means the halting oracle told me P run on P accepts, and that happens when P of P halts. But P of P didn't halt. P of P ran forever. That's a contradiction. That's no good. Okay, clearly it must be the other case. Therefore, P fed P halts. Okay? If P fed P halts, that means H of P fed P rejected. Right? Just by the definition of P. But if H of P fed itself rejects, that means P of P ran forever. And again we get a contradiction. That means we've made a bogus assumption somewhere, and the assumption was assuming that the halting problem can be solved by a Turing machine. We're assuming that H exists. We lead to a contradiction. Therefore, it must be the case H does not exist. Therefore, there cannot exist a Turing machine whose language is encoding of other machines who checks if the machine halts on that input. There can't exist a total Turing machine, that is, some machine H that halts on all inputs that has this property. That means the halting problem is undecidable. There is no decision process that decides in finite time whether a machine fed a string halts or not. And that's what the halting problem is.